kind of where my video stopped here, and it gives you some information about a barometer and all that good stuff. Basically, it's leading to STP, which is standard temperature and pressure, and they give it to you here at STP. Basically, it's at sea level at 0 degrees Celsius, right? So it's 273 Kelvin. Your pressures are, depending on what instrument you use, are going to be 760 millimeters of mercury, and it's abbreviated like that, which is equal to 760 torr, which is another unit for pressure, which is equal to 1 atmosphere, which we abbreviate as ATM, or it's equivalent to 101.3 kilopascals, and that's kPa. Okay, so these are all equivalent, so you can use those as a conversion factor for however you need to convert between whatever you need to convert between in pressure. Okay, and so then this next part, it talks about atmospheric pressure at Mount Everest and how it's higher, higher up, so you don't have as much pressure coming down on you as you do at sea level because there's more room. It's like a difference of 5.5 miles. Okay, so since the amount of atmosphere is so much less on Mount Everest, the amount of oxygen is also a lot less, and most people need supplemental oxygen from a tank at the top. So that will be the case. Like when we went to Ecuador, they're higher up, and it's harder to breathe up there because the oxygen's thinner. Okay, and they talk about a barometer, and they ask you to convert. So an anaerobic barometer right now is used to measure atmospheric pressure to help predict the weather or to measure the altitude. Changes in air pressure signal the movement of high or low pressure areas of air called fonts. Standard sea level atmospheric pressure on your iPhone barometer is 101.3 kilopascals or 101.3 kPa or 30 inches of mercury in our weather reports. Okay, so you can go ahead and do a little conversion here. So in San Antonio, my phone says my altitude is 346 meters. So we're above sea level. As a result, the pressure in atmosphere in San Antonio is less than 101.3 because we're higher up. We're slightly up, a little bit higher. And if you do the conversion, it's 100.7. Okay. And the way you do that is, hey Siri, what's the pressure, the barometric pressure in San Antonio right now?
The barometric pressure is currently 30.04 inches of mercury.
So if you want to convert that, because we need to get it into millimeters of mercury, right? So I want to know, first of all, how many millimeters of mercury are in 30.04 inches of mercury. You can convert this. And I know that this is going to be a couple of steps. I need that. I just know this from doing these conversions all the time. So 1 inch is equal to 2.54 centimeters. I need to get it in centimeters because I need to get to millimeters, right? Because this is inches of mercury, so I need to make that conversion from the standard system that we use here to the metric system. So if I do that, I go 1 inch is equal to 2.54 centimeters. And then I know for every 1 centimeter, there's 10 millimeters. Okay. And so get my little handy dandy calculator. I convert this as 30 times 2.54 times 10. So 30. gives me 763.016, and that would be millimeters of mercury. Okay, that would be my answer here. And now if I need to get it into kilopascals, I use this right here. So for every 101.3 kilopascals, there are 760 millimeters of mercury. So that's my conversion factor. So I want to know how many kilopascals are in this answer right here, 763.016 millimeters of mercury. And then I'm going to use this conversion factor to get in kilopascals. So if I have millimeters of mercury here, I put that on the bottom. And then I put kilopascals, 101.3 kilopascals, and that's 760. So I multiplied this by this, divided by 760. That should give me how many kilopascals in pressure we have. So 763.016 times 101.3. Then I'm going to divide it by, did I get that in there right? 760. Ooh. So we're at 101.7 kilopascals, and that's at what? I say 142 on 331, 2020. That's our pressure right now. It's a little bit higher than 101.3, not by much, and it'll change. Obviously, it was different on this day when I did these notes, and that video got there was no sound on it. So anyways, that's how it kind of worked out. It's kind of a long way to get to this number here, and this one, it's greater than, just slightly greater, just because of the pressure today. So you can do that little conversion every day by asking Siri what the pressure is for the day, and do your dimensional analysis. Okay. So here they're just doing using these conversion factors. That 1 atmosphere is equal to 101.3, 760 torr is equal to 760 millimeters of mercury. This is just all pressures. They're all units of pressure. Okay, and they have this in the notes as well. So I'm going to back up just a little bit. And so this one, it's asked you to convert atmospheric pressure of 273 millimeters of mercury to atmospheres. So I just added this little question mark. How many atmospheres are in 273 millimeters of mercury? And you look over here, and it's 1 atmosphere is equal to 760 torr. So that's a conversion factor here that you're using. 1 atmosphere is equal to 760 torr. And I'm sorry, millimeters of mercury. And then so you just go ahead and run that through. Basically, 273 times 1 divided by 760, and that's how many atmospheres there are at that pressure at Mount Everest. And you can see that it's less than, if you compare it to sea level, much less, because it's so much higher up. Okay, it's not that big of a difference here because we're not too far up from sea level. And they do another conversion factor for you here. They go at the Dead Sea. They want you to go from kilopascals to millimeters of mercury. Kind of the same deal there. Okay, and compare it to 760. 760 is higher than 760 millimeters of mercury at sea level. So on this one, what I want you guys to do is we're going to work this one together. So get out a piece of paper and write these in your notes if you haven't done these. Have Jackson and Devin and Sienna, have you guys already done these notes and you have your answers? Jackson, do you? Devin? Do you have it? I didn't hear. It's good to see you guys. All right, so let's just work this one, okay? So converted tire pressure of 2.04 atmospheres to kilopascals. So they want how many kilopascals are in 2.04 atmospheres, right? And we know that for every 101.3 kilopascals, it is 1 atmosphere, right? Because they're all equivalent. Now we're going between atmospheres and kilopascals. So we're ignoring this. This is our conversion factor. So if I got 8 ATMs up here, then that means I need to put ATM on the bottom, and I need to put kilopascals up top. And this should be 1.0, and this should be 101.3. So when I set that up, I just multiply this times this. ATMs go away. You're left with kilopascals. You're going to want that. And then you should have that answer right there. Right? Did you guys write that? Good? Devin, thumbs up. I can see your light. You good? Okay, sweet. All right, so then on this next one, you're converting a pressure of 570 torr to atmospheres. So then I want atmospheres on this one. How many ATMs are in 570 torr? And this one I'm going to use for every 1 atmosphere. It's 760 torr because they're equivalent at STP, at standard temperature and pressure. So I set up my track, and I got torr up top, right? So I got to put torr on the bottom, atmospheres on top, 760 on the bottom. Then it's all set up. Here's my conversion factor I used. And you should have got 750 atmospheres. Or 0.750, sorry, atmospheres. Which is less than. And then I can use the other side of this. All right, convert pressure of 314 kilopascals to millimeters of mercury. So this is a pressure under 100 feet of water. Very good. So they want to know how many millimeters of mercury are in 314 kilopascals. So in this one, for every 101.3 kilopascals, it is 760 millimeters of mercury. Again, that was given to us here at the top. You're just making that comparison, right? And then I'm going to put this in. kPa goes on the bottom. Millimeters of mercury goes up top. 760 up top. 101.3. So my math is 314 times 760 divided by 101.3. And you should have got a big old number of 2,356 millimeters of mercury. Okay. So getting to the rest of this, they do talk about Fahrenheit a little bit here. I wouldn't worry about that. That's just good information. We always convert from degrees Celsius to Kelvin. Always. So if you want to know how many Kelvin, you just get your degrees Celsius and you add 273. That gives you Kelvin. So, and you're going to need to do that for the notes that we have this week. So let's say in the problem it says the temperature is 20 degrees Celsius, right? So to put it in Kelvin, I would add 273 to that, and it's 293 Kelvin. And I would use this in my equation. Okay, that's very important. Otherwise, you're going to be off all the time. So you're always going to convert between degrees Celsius to Kelvin by just adding 273. Okay. All right, so I printed off. I just wanted to go over a couple of these new notes with you guys today because this is key right here for doing the notes that you guys have for this week. Okay. And there are, we whittled it down to like 4 gas laws that you're going to have to know. There might be one more in there. And this is what was uploaded on Classroom today, or yesterday, sorry. So the gas laws are simple mathematical relationships between volume, temperature, pressure, and amount of gas. And remember, all temps need to be in Kelvin. Okay? So the first one is the only inverse relationship. It's called Boyle's law. You're doing a comparison between pressure and volume, and there's always going to be a change in one of those. Okay, change in pressure or volume that you're solving for. Okay, there's always going to be that. So Boyle's law states that the volume of a fixed mass of gas varies inversely with pressure at a constant temperature. So temperature is going to be your constant here, so that's why it's not in this. So you're going to assume that temperature is constant. It's the same. Okay. So it says P is for pressure. That one's easy. Volume is in milliliters or liters, and temperature is constant. And when you're doing these practice problems, you want to list all your variables for the solving of the gas laws. And I always call that my given. So as you're reading these problems, and if you print this out, you don't have to print it out, but if you're reading it, you're going to mentally take note. So you're going to read this. It says, a sample of oxygen gas has a volume of 150 milliliters. When its pressure is 0.947 atmospheres, what will the volume of the gas be? The pressure of 0.987 atmosphere if the temperature remains constant. So temperature is constant, so that's not going to be an issue. You have your V1 here. This is your P1 there, and this is your P2. So as you read this, you go, all right, what's my V1? It's 150 milliliters. And P1 was what, 0.947? P2 is given here, 0.987, was it atmospheres? And V2 is what they're asking for. So here's your formula that you're going to use. P1, V1, V2, P2, V2. And there is 2 ways you can work this. You can just do the algebra and rearrange the variable to solve for that variable, or you can just make whatever variable that you're solving for X, and you just do your cross multiplication stuff that you learned like in 8th grade to solve for X. Maybe it's 6th grade, 7th grade. Okay. So here's my equation. I'm going to substitute. I want to solve for V2. So to get V2 by itself, I need to divide both sides by P2, right? And so then my equation becomes P1 V1 over P2 equals V2, right? Or you can solve for X and you just plug in your numbers, right? And so V2 is X on this one. So this is one way. The second way, I'll solve for X up here, whichever you're more comfortable with. is how you're going to do this. It doesn't bother me one bit, okay? Just as long as you get it. So my P1 was what? P1 V1 equals P2, and we're solving for V2. So V2 is equal to X. I just write in my numbers. P1 is 0.947. That's atmospheres. And then V1 was 150 mLs. And P2 was 0.987. And then run out of room, that was atmospheres. And we're going to make this X. So if I do it this way, that's just the setup. And then basically you're going to multiply those. I'll just go ahead and do it real quick. So 0.947. 0.947 times 150 and equals that. So you get 142.05 equals 0.987x. So I divide both sides by 0.987 to get my answer. And my x is equal to, and I'm just going to write it here, divide that by 0.987, and you get 143.9, which would round up to 144 when we saw them for volume, so that was liters. Either one of those would be good. Okay, so if I did it the substitution way, then I plug in my numbers. If you're more comfortable with this, my P1 was 0.947 atmospheres, and then my V1 was 150. That should have been milliliters. Sorry, milliliters. 150 milliliters with a decimal there, so you have 3 sig figs in there, and equals V2. And then P2 was 0.987. And then you basically do the math here, which is 0.947. Let me give you some room. 0.947 times 150 divided by 0.987. And you get the same answer. Okay, so either way you slice it, you're gonna come up with the same answer. Okay, so this will be the last one I'm gonna do with you guys today because we're got about a couple minutes left in our meeting. But I want you guys to go ahead and practice this on a piece of paper. Okay, so it says on this one. Let me just go in a little bit. So a gas has a pressure of 1.26 atmospheres. So there's my P1. Occupies a volume of 7.4 liters. There's my V1. If the gas is compressed to a volume of 4.93, there's my V2. What will be the new pressure to be? So P2 is what you're asked to solve for. Of course, temperature is constant, so we need to do that. So our given is P1 is equal to 1.26 atmospheres. V1 is equal to 7.40 liters. P2 is what they want us to solve for. V2 is equal to 2.93 liters. Okay. So go ahead and quick, I'll give you a minute to try and solve that. And when you substitute that, so P2, what's our formula is P1 V1 equals P2 V2. And so P2, if I get it by itself, is divide both sides by V2 to isolate that. Then my new formula then becomes P1 V1 over V2 equals P2. And then I just like to write that to have my stuff that's on the equal sign on the right of my variable. It's the same formula, right? Then I get my numbers and plug it in, right? If I'm solving for X, if I make P2 equals X, then I just write in my formula, right? P1 V1 equals P2 V2, and I put in my numbers. So it's 1.26 atmospheres times 7.40 liters is equal to P2 is going to make that. We're going to make P2X, and V2 is 2.93. Then basically you're going to be doing the same thing. You're going to multiply these two together and divide it by 2.93 to find out your answer. Okay. Here you plug in your numbers, the same thing. What's my P1? Oh, I wrote it down. It's 1.26 atmospheres. And V1 was 7.40 liters. And that's P2. P2 is equal to that. And then V2 was 2.93 liters. You should come up with the same answer each way. So I'll go ahead and do that. So 1.26 times 7.40 divided by 2.93 to 3 sig figs is 3.18. And we're solving for pressure. What was the unit for pressure? It was atmospheres. Final answer. Okay. Same way here. If I work it this way and I solve for X, it's 1.26 times 7.40. I get that answer, and then I divide it by 2.93 to get X by itself. Same answer. Right? So either way, whatever floats your boat, you can do that. And this is just Boyle's law, and then on the next one, we'll talk about Charles' law. We'll talk about Gay-Lussac's. If I don't make a video, just as you guys can tell, it's just hard to get a quiet spot in here. There's a lot of us in the house. So on these, just remember that your temperature is always in Kelvin. So whatever they give you in degrees Celsius, you add 273. That's going to give you your Kelvin. Okay. And then you work your calculations. All right. And we'll talk about that on the next Zoom session. Is there any questions? Let me stop sharing my screen. All right. Hey, Jennifer, you made it, huh? All right. Is there any questions that you guys have? You're all good, Devin? You guys staying sane? Are you overwhelmed with schoolwork, or are you just overwhelmed with boredom? Yeah. Well, go out for a walk. I don't know. I've been going bike riding with my son, my youngest, and there's a bunch of trails out here by Fox Grove. So when it was raining and stuff, we went out. It was like awesome. It was super muddy, and we had fun. I always take snacks. So we get out of the house. Otherwise, I'm in this spot like all day. Like as soon as, because it's like I'm meeting after meeting, and then I'm like, oh, I got to do stuff. And I'm like, oh my gosh, I've been here all day. So I set a schedule, and the big thing that I would say probably about half of my family is keeping to, maybe a little bit more, is a sleep schedule. Stay on a sleep schedule. Get up at the same time, go to the bed at the same time, because some folks are rolling out of bed at like noon or 1, and like I sent that question out to everybody, and they're like, oh, I don't get up until like 3. I'm like, what the heck, man? So it's like you gotta bite the bullet and wake up early, fight through it, and then don't take a nap. And then, you guys are young teenagers, so you guys can sleep all day, but it does affect your mood, and then the sunlight and all that. And then these little Zoom sessions are fun to see you guys, and see how you're doing. All right. All right. So this was recorded. Just anything that I shared on my screen was recorded with you guys. So I'll figure out how to put that up and in Google Classroom so you guys have it. And then usually my meeting, the time that's really quiet in here is really super early in the morning or really late at night. And then when we're all taking classes, it's just hard for me to make videos. That's why I was so mad when my video didn't work. That I made for you guys. And then hopefully the sound went through on this video, so I got to check that. And if it didn't work, then I'm going to scream. You guys might hear me in Fox Grove screaming. All right, y'all. Take care. Next Zoom session will be Thursday. All right, you guys. Good seeing you. Bye.